Am I live now? All right, so we are live, and now I'm going to share the PowerPoint that I have prepared for this topic on Newton's law of cooling. Thank you. Okay, let me just save it for a while. There you go. Right, so this is the second application of differential equations that we're going to take up. The first one was the composition or decay and growth, or growth and decay, the composition or growth. And for Newton's law of cooling, we have the formula d capital T over dt is equal to negative k capital T minus dA. What are these variables? So the capital T will be the temperature of the object at time t, any given time t. T sub A would be the ambient temperature constant. Let me just shade what I am saying. Okay, this one here, the TA. And then we have the T would be this. Okay, but we're going to rearrange it later. Ambient temperature, what is this? Ambient temperature, is the temperature outside or the temperature surrounding a body. And K is the positive constant of cooling rate, like what we did in the composition and in the growth. There would be this constant, but it could be negative or it could be positive. It depends on what would be the scenario. When it's growth, then it's positive. When it's decay or decomposition, or it's failing or it's decreasing, then it's a negative K. Right? This is just to help you recall. But here it's always a positive constant. That is the cooling rate. And then the dt over dt, the d capital T over dt is the rate of change of temperature. Now, I'm talking about temperature here. This is actually what Newton's law is like. Newton's law of cooling is, let me just make that thicker, is all about the rate of change of temperature of an object, the rate of change on the temperature of the object. So, for example, that object is at room temperature at first, and then after some time, after time t, after certain time t that has elapsed, then the temperature or that body could either be frozen, or it's getting to its freezing point, or it could raise in its temperature so it becomes hotter, or at initial point it is already hot and then you let it cool. So how much time will this object reach the temperature you desire? So this is what Newton's law of cooling is all about. Now, you will have a homework that will be written in your notebook. It's a very practical one. So it says here a bowl of soup is served at 80 degrees Celsius and left to cool in a room temperature, maintained at a constant temperature of 20 degrees Celsius. After 10 minutes, the soup's temperature has dropped to 60 degrees Celsius. Of course, we know that at first soup are always hot. If they're not hot, then we put them in the microwave to increase their temperature, because the soup really makes your throat, and how when it goes down to your tummy, you can really feel the effect of the warmness or the hotness of the food. And especially if you're not feeling well, then that's the best thing you can take, isn't it? Right. So after some time, after 10 minutes, the temperature of the soup dropped to 60 degrees Celsius. Using Newton's law of cooling, determine the rate constant K, and of course the time it takes for the soup to cool to 40 degrees Celsius. So that is your homework. But before you can do your homework, of course, which will be written in your notebook and it will be marked the first day of our final term, then we have to take an example. So I have already defined what the formula of Newton's law of cooling is. So dt over d small t is equal to negative k, the big T, minus T sub A, where T sub A is the temperature around the object. Okay, let's have an example in here. So a cup of coffee, wow, as if I want to drink coffee now. Right, a cup of coffee is initially at 90 degrees Celsius in a room with a constant ambient temperature of 25 degrees Celsius. What does it mean? The coffee is at 90 degrees Celsius, so that is just 10 degrees Celsius drop from the boiling point, yeah? And it is placed in a room that is 25 degrees Celsius. If the coffee cools to 70 degrees Celsius in 5 minutes, determine how long it will take for the coffee to cool to 50 degrees Celsius. Assume that the cooling process follows the Newton's law of cooling. So, what is required in here is the temperature of the coffee, as I have shaded with pink. So the temperature of the coffee to cool to 50 degrees. No, it's not the temperature. I'm sorry for that. The time for the coffee to cool to reach a temperature of 50 degrees Celsius. So this is time. I'm sorry. Now, what we're going to do is to use the formula. Okay. Right. So the formula again is it is dt big T over d small t is equal to negative k T minus TA. Now, what is TA in here? The TA is the room temperature, which is 25. This is 25. All right. That's why dt over d big T over d small t is equal to negative k big T minus 25. Okay, let's go to the next slide. So having the d big T over d small t equal to negative k big T minus 25, we're going to rearrange this one in such a way that all t's big T's together and the rest will be together. This is in relation to the decomposition and growth. What did we do? We have to combine all, or we put all those variables, same variables, in one place, in one side of the equation, and the other one on the other side. So what happens here is we have to kick out t minus 25 at the right side. So we have to divide both by t minus 25. Then doing so, this cancels out and you have dt over small dt over t minus 25. What's next is to multiply both sides by dt, eliminating the denominator of the big dt. So now you will have dt over t minus 25 equals minus k dt. That's why you have this. If you separate the dt and the t minus 25, you're actually having two fractions. One is the 1, I'll write it here, 1 over t minus 25 times dt over 1. Okay, so if you multiply 1 times dt, you will have the dt as numerator. 1 times t minus 25, that will be a t minus 25 denominator. Okay, so I will remove all this one spend time. Anyway, you have the recorded discussion so you can refer back to it later. So now we are clear on what this 1 over t minus 25 d big T is equal to negative k dt all about. Next, you have to integrate and integrate. Why do you have an ln t minus 25 here? Because if you have an ln u, then the u here, denominator, should be the derivative of the u should be the numerator of the fraction. So du over u is the derivative of ln u. So let's take the integral of ln u. ln u, the integral, that will be, hang on, I am mixing up differential calculus and integration now. Right. So in the integration, if you have du over u, that is ln u, right? So if you're going to integrate du over u, then you get ln u plus c. If you're going to get the derivative of ln u, then that would be du over u. Okay? Right. So our u is 1 and our du, it's all mixed up. Our du is 1 and our u is t minus 25. Let's check. If our u is t minus 25, that is d over dt, okay? Then our du is, hang on, I'll say our u is t minus 25. So our du over dt will be equal to 1 because we are going to take the derivative of u in terms of t. So there's only one t here, therefore du over dt is 1. So if that is so, that the du over u is in place, the du is 1 and u is t minus 25, that is in place, then automatically you say ln t minus 25, because ln t minus 25, the derivative is du, which is t, and the u is t minus 25. I hope you understood that. Okay, here. So the integral of 1 over t minus 25 dt is ln t minus 25 is equal to negative kt, because that is minus k dt, negative kt plus c. Now, because we like to remove the ln here, like what we did in the decomposition and decay, then you have to exponentiate both sides of the equation. Exponentiation means that you're going to brace your, oh, there is one missing there. Okay, I'll do it here. You're going to raise all this with e as the base. So it becomes e to the ln t minus 25 absolute equal to e to the negative kt plus c. Having this notation, then you can do t minus 25 ln e on the left side, and ln e is equal to 1, equal to e to the c times e to the negative kt. We did this already before the first application. Okay, so this is what I was saying. T minus 25 will be on the other side and then e to the c times e to the negative kt is the equivalent of e raised to negative kt plus c. Now, last time when we dealt with e to the c, we said that this is the PO. But here, we don't have the PO, right? Instead, we can assign another variable. You can use A, you can use B, you can use C, any variable for that matter, to simplify a double constant expression, because E is a constant and C is a constant. So let's just make that one and then let's call it as A. As I've said, these are arbitrary constants, so you can use any variable, B, E to the C, or C. It cannot be C because there's already C there, or any variable that you want, like D is equal to E to the C if you want. But I'm suggesting that whatever I have discussed in here, then that should be the variables you're going to use. Hence, um, you will have now t minus 25, t minus 25 equal to, you have substituted a for e to the c, so that's an a, and then the e raised to negative kt will be in place. Right. So we like the t to be retain the left side. So that is what we have in here. We move the negative 25 to the other side. So it becomes positive 25 plus the remaining expression on the right side. So that will be the working formula to solve for the temperature with a constant K of decreasing in temperature of the object or increasing temperature, as the case may be. All right, for the next slide. Now we're going to apply the initial conditions in the problem. When time is zero, I should say, when time is zero, the small t is the time, and then the big T is the temperature. So when time is zero, it did not drop yet, nothing has been done, then T0 is equal to 90 degrees Celsius. What does it mean? That is the beginning condition of the coffee. So when the coffee was served, the coffee is at 90 degrees Celsius. It means time has not started yet for it to cool down. In this case, with this formula, T is T of time is equal to 25 plus A minus plus A e to the negative kt. Where did this come from? It came from what we did a while ago here at the bottom, okay? With all the conditions. That's a working formula. And what is the real formula? It is d big T over the difference of temperature with that of time equal to minus K, and then you have the big T minus TA. Okay. Right, so now we substitute our boundary conditions. So T of T is 90 is equal to 25 plus A e to the negative K, and T will be 0 here. That's the initial. Okay, so in number 3, you have to apply initial conditions to find for the constant. So A is equal to, you transpose the 25 to the other side. So you have 90 minus 25, you get 65. Why? What happened to the e raised to negative k0? Okay, let's do the working separately. Or that will be, I'll do it here, 90 is equal to 25 plus a, and then you have e to the negative k times 0. Anything that is raised to 0 gives you 1. So e to the 0 is equal to 1. X to the 0 is equal to 1. A to the 0 is equal to 1. 5 to the 0 is equal to 1. So any number, any letter for that matter, or any expression that is raised to 0 is equal to 1. For example, you have x plus 1 here, and this is raised to 0, that is 1. Okay? Right. So let's remove all this one meantime. That's why here 90 was there already, 25 was transposed, so you have 65. And then where did this go? That is already equal to 1. So you found that a is equal to 65. So substituting the values in our working formula, so T sub t is equal to 25 plus 65 e to the negative kt. Now, we must know what k is so we can calculate the time for the coffee to go down to 50 degrees Celsius. Let's have the next slide. Right, and here, find the cooling rate K. So at T is equal to 5, and the temperature at 5 minutes is equal to 70 centigrade. Where did you get that one? Or where did we take this one? Okay, so let's go back to the problem statement. It says here, if the coffee cools to 70 degrees Celsius in 5 minutes, I always say degrees centigrade because this is how we say it before, but now, of course, Celsius, yeah? Centigrade and Celsius are synonymous, but for the SI unit of um, system of units or unit, system of units, or SI system, then degrees Celsius is the one being used. Okay, so you can see from here the conditions: 7 degrees Celsius in 5 minutes. That is where we have picked the values to compute for several unknowns. Okay, so with the working definition, the temperature at 5 will be 70, and then you have the 25 plus 65 e to the negative 5, and a k will be a variable. So 70 minus 25 will be 45, and the other side you have 65e negative 5k. So what will you do to find for k? Divide 45 by 65. So let's do it here. 45 is equal to 65. I'm running out of battery. Right? So divide both by 65 in time to remove the coefficient of e, and you will have here e to the negative 5k. Let's just switch places, is equal to 45 over 65, or 45 over 65 is equal to 9 over 13. So it's 9 over 13. Because this is a base e, then you can use natural logarithm here. So this could be negative 5k ln A is equal to ln 9 over 13. ln E is equal to 1. So now you can solve for k, and that is divide everything by negative 5. By negative 5, you will have k is equal to negative ln 9 over 13 divided by 5. Okay? Or we can just put the negative, keep it with the 5 because that's where it came from. And now we can use our calculator. We can directly put in our calculator, and it says negative fraction 1 over 5, and you have an ln, and you have a fraction again, and that will be n 9, I should say, over 13, and close bracket, and equals. So you have a k of 0.07354. For our last slide, knowing k to be 0.07354, we can now find the time to cool to 50 degrees. So again, we have to take the working definition with the boundary conditions, 25 and 65. 65 is the A that we have solved a while ago. 25, that would be the room temperature. The K, we know that to be 0.7354. Now what we only have left is T, but T is given to be, no, that is the one unknown, I should say. And T sub T, this is 50 degrees Celsius. So all of these are known except T. There's only one variable left. So I have already the calculations here, but I still want to discuss how it was done. So T sub T, that will be 50, and then is equal to 25 plus 65, and then you have base E, you have negative 0.07354, and T is left there. So what you're going to do, transpose the 25 to the other side. Transpose it here. So 50 minus 25 will only give you 25 after. And then 65 e to the negative kt is left on the other side. Divide both by 65. So you will have 25 over 65, or that is 5 over 13. So you are left with e to the negative kt equal to 5 over 13. Like what we did earlier on, you can use natural logarithm calculations here, or principles. So negative kt ln e, that is equal to 1, is equal to ln 5 over 13. Knowing k to be 0.07354, t can already be solved. So you will have t equal to ln 5 over 13, and then you have to divide both by minus k, or that will be negative 1 over k. Okay, so this is shown in here. So put that in your calculator. What you're going to write in your calculator will be this. So we must get 12.993 minutes. So that's the time for the coffee to cool down until it reaches 50 degrees Celsius. So let's do it here. We have a fraction, of course, and that is a negative 1 over 0.07354. And you have an ln, or natural logarithm, in fraction form, so that will be 5 over 13, and close it, That's it. And then equals. So that's how the 12.993 minutes, um, that's how the 9.55, 12, sorry, 12.993 minutes was arrived at. Okay, so this is what you're going to do for the DE homework that you will be writing in your notebook, which is about the Newton's law of cooling. So please don't forget your homework and just follow the procedure I have in this video. But I have to send you now. I know it's 12:28 in the morning. It's very late for me to do it because we had a brownout a while ago. So I have to wait for the electricity to be restored because I cannot sleep without finishing this work. Okay, because we were ordered to do a synchronous lesson with you guys. So this is an asynchronous teaching as well for me because this is the only time I can do it. Well, I had morning, but of course there are other concerns that I need to attend to. Sorry for the very early morning um, sense of the video and also the copy of my lecture. Okay, so I'll end from here. Bye for now. Have a great Tuesday. Is it? No, it's not Tuesday. What? Wednesday, I should say. Great Wednesday. It's already the 20th of November. And we will be at the uni as usual. But of course, there will be no students because classes are suspended. So just get ready with your midterm exam, and I'll see you during the exam stage. Okay, so please do your homework. We already have two applications. I will be sending more videos and lecture notes on applications of DE because, as I've told you, this will only be the coverage. All applications of DE will be the coverage for the final term, and it will be multiple choice type. Okay, right then, bye for now, and I'll see you during the exam. Bye. Bye. Sorry.